this lecture, let us see the properties of wave function. So we have seven properties of wave function. So with the detailed understanding, we will get to know the seven properties. So the first properties is that the wave function psi of rt is a complex valued wave function. So basically, it is a complex function. Um, so you may write in terms of real and imaginary parts like this. Suppose A is the uh, real part. Now here A and B are real functions. Real functions. Um, Now complex conjugate of this complex function will be A, and when we multiply wave function with its complex conjugate, we will get a square plus b square. That is so this will be is equal to absolute value of psi square, and this value is always real. So this value, it is always real and positive because it is square of the absolute value. So square of any real value is always positive. So this is the first property of wave function. Now let us see the second property. So so the wave function, it is a mathematical description of the quantum state of a particle. So it is function of momentum, time, position, and spin. And so this is a mathematical description for the wave function. But how about the physical description? There is no physical description for psi of rt. No physical interpretation. Now, but what about the absolute value of psi square? This has physical interpretation and it gives the probability of finding a particle at a given time. Particle in space. So this is a Bond's interpretation of the wave function. That is absolute value of psi square is the probability of finding particle in space. And next important property of the wave function is about its normalization. So what do we mean by normalization? Basically, the integral of psi square over all x. So when we take all the space, that is from minus infinity to plus infinity, and absolute value of psi of x comma t whole square dx, then this should be 1. And here the wave function would be determined by the Schrodinger equation. Suppose if psi of x comma t, so just we are considering one dimensional case, but it is also applicable for three dimensional case. Just for simplicity, we are taking we are just understanding in one dimension, so the same can be applied to three dimension. If psi of x comma t is a solution of a Schrodinger equation, then in this case, if we multiply a with psi of x comma t, if we multiply a psi of x comma t, then this is also a solution of a Schrodinger equation. So where here a is um, it is a complex constant. Now when we do this, this will help us to normalize the wave function. So here a is a factor, and uh, by multiplying this factor with wave function, we can normalize the wave function. Now, for example, when Schrodinger equation is solved and consider a solution like psi of x comma t having a value of infinite. So, what does imply? That implies that suppose if psi of x comma t um, gives some infinite value, suppose if it implies, then there will be no multiplicative factor for this wave function. In that case, no multiplicative factor, because for normalizing. So, as there is no multiplicative factor for normalizing, then this cannot be a solution. This wave function cannot be a solution for Schrodinger equation. Similarly, if psi of x comma t equal to 0, uh, then this also cannot correspond to uh, Schrodinger equation, because there will be no multiplicative factor in this case as well. Hence, this is also not a solution. So, psi of x comma t having a solution of infinite value, nor trivial solution like 0, these two cannot be considered as solutions to Schrodinger equation, because there is no multiplicative factor for normalizing the wave function. So, so basically these are non-normalizable solutions. But only the physically realizable states, only those correspond to the solutions of the Schrodinger equation. Now, if psi is normalized at time t is equal to 0, if psi of x comma t is normalized at t is equal to 0, now as time goes on, that is for t greater than 0, the psi of x comma t will keep on evolving. This will keep on evolving with, as it is function of time. So we can't keep renormalizing the multiplicative factor. So in that case, multiplicative factor also uh, would be changing if we keep renormalizing. But the property of Schrodinger um, equation is that whatever the solution, that wave function psi of x comma t, um, so it is normalizable for all the time t greater than 0. That is, the normalizing property is preserved for all time t greater than 0. And so that mathematically that implies, so mathematically what does that mean is, when we differentiate this d by dt of minus infinity, so this has to become 0. We have to prove that this is 0. So um, so what does this imply? The thing which I have said previously, that is preserving the normalization property. Preservation of normalization of the wave function. So I'm writing psi for t greater than 0. That is as time. So so what does this? If you look both the text here and the equation, when we differentiate d by dt of this one, then it is equal to 0. That means when we are differentiating with time, it is equal to 0. That implies it is independent of time. That is, it is not varying with time, rather it is staying constant. That's why differentiation here is 0. So that's interpretation is that preservation of normalization of the psi for t greater than 0. Now let's prove this one, how this is achieved. So we know that modulus of psi of x comma t whole square, the thing which is here, is equal to, I don't want to write every time the function of x comma t, so I'm just putting psi just to save the time. Um, Now, okay, this is the thing. Now, when we take this d by dt inside, it will become. Um, okay, let me draw a line here. So, when we take d by dt here, it will be dou by dou t, because as psi is function of x and t, but we want only differentiation with respect to time t, so it has to be partial derivative of time dx. Now we have this, so this will be is equal to, we have shown here that it is equal to product of wave function and its complex conjugate. Now what is dou by dou t of this will be is equal to, plus sign. And from Schrodinger equation, in the previous lecture also we have shown that dou psi by dou t equal to minus I h cross by 2m dou square psi by dou x square. So basically rearranging the terms in time dependent Schrodinger equation. So this is a time dependent Schrodinger equation. Just rearranging the terms here, bringing IH cross to the right hand side. Now complex conjugate of this would be IH cross by 2m dou square psi by dou x square plus I by h cross v psi. Now we have this. So for this we have this. Um, okay, so dou dou by dou t of psi square. This will be is equal to, so here this is psi square and likewise for this. But I want to substitute for dou psi by dou t and dou psi by um, dou psi conjugate by dou t. So we get psi star and dou psi by dou t is minus IH cross by 2m minus I by h cross v psi. So there is minus sign here plus psi and here we have this. E times psi. So we got this now. Um, Let me wipe some space. Here, let me wipe this side. Mm, so sorry, here dou square by dou x square is there. What? Let me rewrite this again. Basically, it's a conjugate of this term. So minus IH minus I by h cross. Sorry, I by h cross v psi. So here you can see that psi multiplied with psi conjugate, and here also psi multiplied with um, let me let me rewrite this equation. So the Schrodinger equation is dou psi by dou t is equal to minus I h cross by 2m dou square psi by dou x square minus I by h cross v psi. Now when we take conjugate of this, it will be minus I h cross by 2m dou square psi conjugate. Sorry, here it will be plus by 2x square plus I by h cross v psi. Now when we substitute this here, this will be uh, conjugate. Now we have to rearrange these. So yeah, we can use this space here. Okay. Now you can see here psi times psi conjugate, and here also psi times of psi conjugate, and plus and minus here. So these terms of potential will get cancelled, and we end up with uh, dou by dou t of psi square. This is equal to, take psi, when we take this. So basically we have dou by dou x in two cases. So we can take that as common. Dou by dou x, and we have ih bar common by 2m. Um, Now for this we can take psi star. Let me remove this as so psi star dou psi by dou x. So this is equal to this. So basically we are, when we simplify this equation, we end up getting this. If you differentiate this one, it will expand to this equation. Basically adding and subtracting this potential term. Apart from that, you end up getting this one. Oh, okay. So we got this dou by dou t of. So let's plug into the equation. Then that will be. Um, so basically we have seen that this is equal to dou by, sorry, minus infinity to infinity dou by dou t of more or less x comma t whole square dx. This is equal to, now we got dou by dou t of square here. So then what we can do is we can substitute the above equation, that is this is equal to this, so dou by dou x of I h cross by 2m times dx. Now here we have differential and integral, so the differentiation will go, and this will give us uh, I h cross by 2m. Here minus infinity to plus infinity, but we know that as x tends to infinity, then psi vanishes. So when psi vanishes, all we get with this is equal to 0. Hence we proved that d by dt of this is equal to 0. So there is preservation of normalization of psi for t greater than 0. Now let's go to another property of wave function, that is psi of r comma t and the first derivative of psi of, so basically it is derivative for three dimensions Laplacian operator, and it must be continuous. So the wave function psi has to be continuous, so that means we have for example, this is consider in only one dimension. It is applicable for all dimension. So the wave function must exist everywhere. But for example, let's take at x equal to 0, there is infinity potential barrier here. Infinite potential barrier. So if there is, then psi won't exist at this infinite potential barrier. Rest the psi will be continuous all along. Suppose if there is another infinity potential barrier here, it will become discontinuous. So it is continuous everywhere except at infinity potential barriers. The other property of that is psi of rt is single valued. Means if we have a graph like this for psi and this is x, so we have only one, so the wave function could be like this. So there is uh, so this at this point for x equal to 0, sorry, for x some particular x we have two values. This is not the psi. Psi should have a single value, so this is not the one. But if we take another case like this, um, maybe like this, so something, but it should be having only one value for any um, space coordinate, and psi should have finite value everywhere. That only implies that the system is physically realizable, or then only the system is physically possible. So only this is physically possible. then only psi of or this will give probability of finding the particle. The seventh property is orthogonality of wave functions. So if there are two wave functions, psi n of x and psi m of x, these are eigenfunctions of Hamiltonian. I will explain what are eigenfunctions of the Hamiltonian. So, an eigenfunction is something that correspond to an energy level. Here we have two eigenfunctions. That means they correspond to two different energy levels. Eigenfunctions of the Hamiltonian of two different energy levels. Basically, M and En. Sorry, firstly we have taken. So let's take En and then En. So here n is not equal to m. Then the property is that minus infinity to plus infinity. So this implies that these two quantum states are independent quantum states. Basically, one doesn't influence the other quantum state. So the physical interpretation of this is quantum states are these two different quantum states are independent. So in quantum mechanics, the orthogonality is the property which allows us to expand the wave function in terms of its eigenstates. So what are the eigenfunctions of the Hamiltonian in quantum mechanics? Um, the Hamiltonian, let, just let me. So the Hamiltonian represented by H with a hat, it represents the total energy of quantum system. And it is given as h hat equal to p hat square by 2m plus phi of x hat. P hat is the momentum operator minus I h cross dou by dou x. So this is a momentum operator and v of x is a potential energy. Now, when we write the Schrodinger time independent Schrodinger equation, En times psi n of x. Similarly, for m is another quantum state. Um, so we can write Em into psi m of x. These two are two different eigenfunctions. So it corresponds to two different energy levels, or eigenstates, En and Em respectively. Now these two states are independent. That is the property, and that property is determined by orthogonality as this. Sorry. Um, Let me not write that. By default, you may assume it is a function of space time. So is equal to 0 for n not equal to m. So this is what this implies. So physical meaning of this is that the two eigenstates are independent, and corresponding eigenfunctions and eigenstates are related in this manner. Eigenstates, oh sorry, let me, eigenfunctions and eigenstates. mm, are related in this way. So here eigenstates are Em and En, whereas eigenfunctions are psi m, psi n, and their relation is in this manner, and both eigenstates are independent. That is given by this orthogonality property. Um, so let us see some um, eigenfunctions for different potentials. We have seen that. So this is a case of Hamiltonian. In this case, potential energy is zero for free particle. Some examples I am giving of the potential energy. So if the particle is free particle, P of x is zero. Hamiltonian will be plus zero because potential is zero, and this is equal to minus. Now when we solve the equation, is so this is we know that E is real, and we have psi here. Okay, so E is real and H is also real from this. Now in this case, what are the possibilities of psi? Okay, in this case, the possibilities of psi um, are basically plane waves. Eigenfunctions are plane waves in this case. That means the wave function psi is a plane wave in this case, is a plane wave. The second case is that v of x is infinite potential well. So basically, it is 0 for otherwise. So we have some x axis. So this is infinite. And we have length L for which the potential is 0 in this duration. So this is 0 and L. Now for this, the eigenfunctions are these are the wave functions corresponding to this potential case. So here the solutions are the solutions of Schrodinger time independent equation because the potential is not dependent on time. So this corresponds to Schrodinger time independent equation. The same in the case of free particle, we need not even worry about time because the potential is zero. Neither potential has any value even to make sense of what it is function of. So in that case also time independent Schrodinger equation by default. That's very obvious in that. Now let's take a harmonic oscillator. Third example. In this case, potential is by m omega square x square, and the eigenfunctions or the solutions of time independent Schrodinger equation is given by. So this is a Hermite polynomial basically. We will see in the further lectures what it is. But I'm just giving some idea to proceed further. Anyways, if you remember that orthogonality for this lecture, if you understood the property, that's well enough. And this is giving some basis for next lectures. Okay. And in this case, the eigenstates will be n plus 1 by 2, which okay. So we can understand and derive, solve these cases in further lectures. But for now, I have you have seen what are the seven properties of wave function. Thank you so much for watching, and please do subscribe to get more videos. Thank you.